All right, hello one more time. Today we're going to do section 4.9, which is on something called Markov chains. And so it's kind of an interesting application thing. Anyway, so if you have a highlighter or something, maybe highlight this little part right here. So suppose a physical or mathematical system undergoes a process of change such that at any moment it can be in one of a finite number of states. Okay, so for example, the weather could be sunny, cloudy, or rainy. And then you have, then the next little thing is, suppose that such a system changes with time from one state to another, and at scheduled times, the state of the system is observed. So like at the beginning of every day or something. Now, this also depends on basically knowing the chance of something happening and then the next thing happening being dependent on that type of thing. All right. So this next little bit, if the probability of a given state can be predicted by just knowing the state of the system at the preceding observation, then the process of change is called a Markov chain or Markov process. All right, so those are the things that we're going to be doing, and you'll see what it means in some of the examples down here, or see what I'm talking about. But there's some just little notation here. Right, so what you're going to be doing is putting basically probabilities in this little in your matrix right here, and you're going to have kind of like a before and an after. Okay, and when somebody in this little definition, this little P13, what that means is that the probability of the new state, and by new state meaning like the probability of what happens next, basically, given the preceding state. Like if for some reason, like, oh, it rains one day, and based on if it rains on Wednesday, then on Thursday it's going to have a chance of being sunny or raining again. So like basically things kind of are dependent. All right, so this is the first example that we're going to go with, and here we go. So this example, Rent-A-Lemon. Rent-A-Lemon has 3 locations, like a car rental place, right? And so there's a funny name, haha, right? All right, 3 locations from which to rent a car for one day. You can rent it from the airport, their downtown location, and the valley location, all right? And so when you rent it from there, you have the option of returning it to any of those 3 places. And so that's what this matrix is going to represent down here. All right, this is a daily migration, kind of like your movement in a way. So, you know, migration is like your movement. All right, so basically what this chart is saying, so if I look at like this number, that means 3% of the cars rented from the airport right here are going to be returned to the downtown. If I look at this right here, 8% of the cars rented from the downtown location are going to be returned to the valley location, and so forth. All right, so that's how you read that table. So this is called our migration matrix. Okay, so that little definition right there. All right, so note that the probabilities in each column total 1. So basically, you know, you need to cover 100% of where these things were rented from. These all total 1. And so that is like a, you know, a little important fact, right? So the probabilities total 1. And a matrix with this property is called a stochastic matrix. So that's what we're going to be calling it from now on. All right, and so when I do this in the problems, I might do something like, you know, stochastic matrix, I'll just put like SM, so I don't have to keep like writing it over again. Okay. All right, so here's our initial state vector for this problem. And it says initially we got 50% of our cars, like we're going to start the week with 50% of our cars at the airport, 30% at downtown location, and 20% at the valley location. All right. And so we want to know, like, where are their cars going to be? Like, where can I expect the cars to all end up? Like, how many workers maybe should I deploy to each place given this information? And, you know, all these numbers are based on past history and things like that. All right, so basically we have our matrix that we have, our probabilities. We multiply it by where everybody was to begin with. And then you can see right here, this problem's all worked out. You can see your answer right there. So basically 49% of your cars are going to be at the airport, 29% are going to be downtown, and 21% are going to be at the Valley location. So this happens like day after day after day. And so maybe, based on the number of parking spots you have, or, space or workers, maybe there is a certain number of days that go by that you need to like reset everything, like move everything back, or, whatever it might be. All right, so what happens here, though, if you keep doing this, so basically what you do, this becomes like your new state vector. So that's going to go right here, and you're going to multiply it by your stochastic matrix, and then you get what happens where everything is on day 2. And then you take that answer, you put it there, and then you get everything on day 3. And then you take that answer and put it there, and then here is after day 4, like where are all the cars. But if you keep doing this, so if you do this, look, it said 49 times, 50 times, look at these answers. They stay the same. So when you start to notice that they stay the same, that is called your steady state vector. Okay, and that's what you're kind of looking for. Like, what's going to eventually happen after all this time. Okay, all right, so we're going to do that in this next example. And here we go. So by reviewing its donation records, the alumni office of a college finds that 80% of its alumni who contribute to the annual fund one year are also going to contribute the next year. So this is what we have going on. We have our matrix right here, our migration matrix. We basically have these people donate, and this is now, and this is next year or later. They either donate or we'll say not donate. All right, so 80% of the alumni who contribute one year are also going to contribute the next year. So those are donate. So that would be 0.8. All right, and remember the columns have to add up to 1. So once I know that is 0.8, this is 0.2. All right, and then it says that 30% of those who do not contribute one year won't do it the next year either. So that one, 30% who do not contribute, so they will contribute the next year. So this 0.3 goes right here and then adds up to 1, so this is 0.7. All right, so I'm not going to show you all these things. You can do this on the calculator, but this matrix right here that we have is going to stay the same, and we're basically going to figure out when it's going to stay stable. All right, so construct a transition matrix and initial state matrix. So basically what's happening right now is 80% of the people are donating and 20% are not, and I want to see what's going to happen later. So I'm going to take my stochastic matrix and I'm going to multiply it by my initial state, which is 0.8 and 0.2. All right, so this is going to be after 1 year. So after 1 year, you multiply this guy and that guy, which is what my SM and this is you get 0.7 and 0.3. Okay, so then for the second year, I would take the stochastic matrix again, but then I would multiply by this new one because that's where I am now. So 0.7 and 0.3. And then you get 0.65 and 0.35. Okay, all right. So the first 5 years. So basically you keep doing that, doing it. I'm not going to show you all of them. But anyway, when you get to X5, you still have your stochastic matrix. And X4, the answer was 0.6125 and 0.3875. So my final answer for 5th year is 0.606 and 0.394. Okay, all right. So it turns out that if you do this a few more times, like 5 or 6 more times, you get to your 11th year and it basically stays the same. Like you get, it's not really changing. You get 0.6 and 0.4. Okay. All right. So that's the answer to the question. And so basically over time, they can see that they're going 60% donate and 40% don't. All right, so this is kind of a pain, like, and you're like, oh, how many times am I going to have to do this? How long am I going to have to wait? And so you kind of want to know like what's going to eventually happen anyway. And so there is a better way to do this. So what we're going to do is what's happening here is you come to a point when you notice that things aren't changing, just like over here, like nothing changed, nothing changed, nothing changed. So our steady state vector kept coming out. Nothing was changing, even though, because I was multiplying the same numbers by this again. All right. So we basically have this presumption right here. M times X equals X again, which is what we've been getting. All right. So what happens here? The next line, put a little I right there. So remember, I is your identity matrix. Remember, if you multiply your identity matrix by a vector, then you just get the same thing back again. So it's like, it's like saying that, 6, it's like saying, 6 equals 6 and putting a 1 right there. Nobody really cares because 1 times 6 is 6 also. Okay. All right. So then moving this over to the other side to create this, then factoring out the X to create this. And so this is something we can solve. We have a matrix, which is our migration matrix, migration matrix minus the identity matrix times X equals 0. So what we can do is we can put the migration matrix minus the identity matrix, and we can solve it. We can do an augmentation with zeros, however many we need, and that'll be the answer for X. And so we don't have to do this whole big long process all the time. All right, so let's try and do that. All right, so we're going to find a steady state vector for this matrix right here. All right, so the first thing we want to do is we want to subtract the identity matrix from this because we're trying to do that whole M minus I part. All right, so the 3 by 3, I have 1, 0, 0, 0, 1, 0, 0, 0, 1. So when I do that, I get negative 2/3, 1/2, 0. I get 1/3, negative 1. I get 1/4. I get 1/3, 1/2, and negative 1/4. So remember, we are trying to say that this times X equals 0. So we're going to set up a matrix with M minus I and augment it with 0, and we're going to solve it. So let me just augment this. Erase my equal sign. I'm just going to augment this with some zeros and put that into my calculator and RF it. So when you RF that, you get 1, 0, negative 1/4, 0. You get 0, 1, negative 1/3, 0. And you get 0, 0, 0, 0. So you can see if I write my answers here, I would have x1, x2, x3. x3 is free, so x3. x2 is 1/3 x3, and x1 is 1/4 x3. So everything basically depends on x3. So basically what I have going on right here is I have that x is just something, this 1/4, 1/3, and 1 times x3, right? All right, so we need to do a little trick to this. We need to see how many parts of a whole this thing is. So what I'm going to do is I'm going to, I can choose x3 to be anything. So let's choose it to be 12. So we're going to choose x3 to be 12 so that when I multiply 12 by all these things, I get a nice integer. All right. So if x3 is 12, I get x equal to 3 and then 4 and 12. So I can see how much weight each one is holding because my steady state vector has to be probabilities all adding up to 1. All right, so what I can see is that 3, 4, and 12 add up to 19 parts. So this adds up to like 19 parts. The first one counts for 3 out of those 19 parts, so 3/19. The second one counts for 4 of them, so 4 out of 19. And then the last one counts for 12, so 12 out of 19. So that right there is my steady state vector. All right, so let's do this last one here. And before I forget to mention, your homework is just in section 4.9. It is numbers 3 and 13. They're kind of based on each other. So, all right, so here we go. So I'm given the steady state I'm sorry, this migration matrix here. So suppose that 3% of the population of the U.S. lives in the state of Washington. Suppose the migration of the population into and out of Washington state will be constant for many years to the following migration probabilities. What percentage of the total U.S. population will eventually live in Washington? All right. And so you don't even have to know what the population is. They're just looking for a percentage. All right. So basically I have to take this matrix, subtract the identity matrix of the same size, all right, and that's going to get me to this point right here. All right, so that would obviously be 1, 0, 0, 1. So when I do that, I get 0.9 minus 1, so negative 0.1. This 0.01 right here just stays the same. Down below, my 0.10 stays the same. And the 0.99, I'm doing 0.99 minus 1, so negative 0.01. All right. Okay, so now all we have to do is augment this with 0 and RF it. And so when you RF it, you get 1, negative 1/10, 0, 0, and you get 0 and 0 there. So if you write this out, you have x1 and x2. x2 is free, so x2. x1 is 1/10 of x2. All right, so if you can kind of put this in a vector format, you have 1/10 and you have 1. This is all times x2. This is my answer. This is my answer for x. All right. So if I make x2 10, how about? So I'm going to set that equal to 10. So that means that this becomes 1 and 10. So that way I can see, oh, I have 11 parts. So if I have 11 parts, the top one has to count for 1/11 of it. The bottom one has to count for 10/11 of that. So you have to make it like into a probability vector. And there's your steady state vector. All right, so that means that 1/11 of the population will live in Washington state and 10/11 will not live in Washington state, so outside. Okay, and that is it, and I'll talk to you next time. Bye-bye.